Binary logistic regression with continuous predictor or binary predictor or categorical predictor or ordinal predictor in SPSS. Binary logistic regression with a continuous predictor in SPSS. Binary logistic regression is a statistical method that can be used to find whether there is a relationship or association between two variables. One of the variable is the outcome or the response variable or the dependent variable, and the other variable is the explanatory variable or the independent variable or the exposure variable. To perform binary logistic regression, the outcome or the dependent variable have to be binary or binomial. Binary or binomial variables mean that there are only two categories. An example is whether you smoke, yes or no. You do have diabetes, yes or no. You do have heart diseases, yes or no. To use this statistical test, the outcome should be binary. The predictor can be a continuous variable, or it can be a nominal variable, or it can be an ordinal variable. A continuous variable is measured at a continuous scale, such as weight, height, blood pressure. So it could be measured at an interval or ratio level. The nominal predictor or variable is a categorical variable which can have categories in it, such as occupation, whether you are a doctor, dentist, pharmacist, and so on. The ordinal variable is a categorical variable but with order in it. So the classes are ordered, such as age classes. So to perform binary logistic regression in SPSS, I had inserted data here for 100 participants. There are two variables here. The first one is the age, the second one is the heart diseases. If I click on the variable view, the age is a scale, measured at a scale level. The heart diseases is given a values and label, 0 for no heart diseases and 1 for heart diseases. And as shown here, we have here an outcome or a dependent variable, which is heart diseases, whether you have a heart diseases or no heart diseases. So it is a binary variable, binary outcome. And the age is a scale, so it is a continuous variable. So here we have two variables. One is binary, which is an outcome, which is heart diseases, and one which is continuous, which is a predictor. So if we want to find out whether there is association or link between the age and the heart diseases, or whether the age can predict the probability or the possibility of getting heart diseases, then binary logistic regression test is the best to do for this type of data. Before moving ahead to perform the test, let's look at the range for the values in the age group. If we click and analyze, then descriptive, statistics, frequencies, reset this. Let's bring the age to the variables, and let's bring heart diseases into variables, and then click on statistics here. Let's select minimum and maximum. Click on continue. For format, nothing to choose from, and chart, nothing. And if I click on OK, a table is generated here as shown. There is no missing values. There are 100 valid cases or participants. the minimum for the age participating in this analysis are 18 years old, and the maximum is 94 years old. As shown here for the final table for the heart diseases, those who do not have heart diseases are 44%, and those with heart diseases are 56%. To perform binary logistic regression, click on Analyze, scroll down to Regression, then select the binary logistic regression, reset that. As already we knew that the outcome, which is the dependent variable, is the heart diseases. Drag that into the dependent area, and for the age it is continuous variable. Any variable can be dragged into this box. Since the predictor here, the age, is not categorical, so we do not need to use this icon and this window. But if we click on options, I'm going to select the classification plot, Hosmer goodness of fit test, and see confidence interval for the exponential b. If I click on continue and then click on OK, an output is generated with several tables and diagram. From the first table, it is shown that there are 100 cases in the analysis. There is no missing cases. For the second table, it is the dependent variable coding. So 0 is given for no heart diseases, 1 is for heart diseases, which is very important, essential to recognize this, because this is the 0 will be the reference group to compare to, bending on this diagram as it's shown here. Predicted probability is of membership for HD. So we will compare this one to this. So the 0, the no heart diseases will be the reference group. The next table shows the classification that there are 44 cases of no heart diseases and 56 heart diseases. The next table is variables in the equation. So this is the b here for the coefficient, and significant here is also important, and the exponential for the odds ratio. And Wald test has been used to perform the analysis. SE for standard error and degree of freedom. The most important thing is to look at is in this section here to the table which is labeled as model summary. The model summary here have 2 R square. We will stick with this 1 R square. It shows that the R square is equal to 0.77. This means that 77.5% of the variation in the outcome, which is heart diseases, can be explained by the predictor, which is the age. The next table is the table for the Hosmer test. Again, we need that table, the significant in it, to be greater than 0.05 as shown here. The most important table to look at for the analysis is this one here. Before interpreting this table, as I said here, we are looking at predicting the heart diseases relative to the no heart diseases. In the table here, the first one is the p-value, which is the coefficient. The other important value here is the exponential, which is the odds ratio. 95% confidence interval for this odds ratio is given here, significant value is given here, and Wald test value and degree of freedom. The way to read the result here is that there is a significant association between the age and the heart diseases, possibility of getting heart diseases. Though heart diseases is not given here, but it's already known that the analysis is for heart diseases. So this row here for the age, and it shows that if we look at the value here, with every unit of increase in age, which is 1 year, every 1 year increase in the age, there is a 1.2 odds increase in the possibility of having heart diseases. In another way, for every year of increase in an individual or a person, there is a 20% increased chances of getting heart diseases. 20% is calculated by subtracting this 1.2 from 1, which will give us 0.2. Multiply that by 100%, it will be 20%. So there is an increased chance, 20% increased chance of getting heart diseases with increasing age. So this is the way to do logistic regression, binary logistic regression, for a predictor that is continuous and for an outcome that is binary, whether you have a disease or not, to find out whether there is association or relationship or a link between these two variables, and whether the predictor can predict the outcome, which is in this case the chances of getting heart diseases. Binary logistic regression for a predictor that is binary in SPSS. Here in this SPSS data sheet, I had inserted 100 cases or participant. There are two variables here, one for gender and one for heart diseases. So the first one, which is the gender, is a binary or binomial variable, have two levels in it, males or females. If I click on the variable view and click on the values for the sex, 0 is assigned for females and 1 is assigned for males. So here we have one variable which is binary or dichotomous, have yes or no, or have male or females in it. 1 for male and 0 for females. The second variable, which is heart diseases, whether you have a heart diseases or not. If we click on variable view, then in values, and the 0 value is assigned for no heart diseases and 1 is assigned for heart diseases. So here we have a variable which is binary. If I click on that icon, you can see it's coded 0 or 1. So here we have two variables. One of the variable is the outcome, which is the heart diseases, whether you can get a heart diseases or you will not get a heart diseases based on the data inserted here. So to find out whether there is association or relationship between the gender and possibility or probability of getting heart diseases, binary logistic regression can be performed. And the condition for performing that test is fulfilled, as there are two variables. One of them is the outcome, which is binary, and the other one, which is a predictor, which is also a binary. Before we start, let's check the frequency for each variable. If we click on Analyze Frequencies and then drag the 6 to the variable box and the heart diseases, click on Statistics, and nothing to choose from here. Let's just click on OK. Again, multiple tables are generated. The first table shows that there are 100 cases with no missing values for sex and heart diseases. For the first variable, which is the predictor, which is the sex, there are 52% of female and 48% of males. And for the heart diseases, 44% have no heart diseases and 56% have heart diseases. To perform logistic regression binary, click on Analyze, scroll down to Regression, and then scroll down and select the binary logistic regression. Reset that window, and in that window, since we know that the heart diseases is the outcome or the dependent variable, this is the variable we want to find out whether the predictor, which is the sex, which is a binary, can predict probability or possibility of having heart diseases. Drag that into the box here. Since we have here a predictor that is binary or categorical, click on categorical, drag the 6 here. Although it is just having only 2 levels in it, I'm going to set the 0 for the first, which means that male will be compared to females. Click on continue. For options, I'm going to select classification, plots, Hosmer, goodness of fit, and confidence interval for the exponential p. Click on continue, click on OK. Multiple tables are generated. The first table shows a summary for the case or cases. As shown, 100 cases, no missing values or cases. The second table is the dependent variable, which is the outcome, which is the heart diseases. As shown here, it has been given a value of 0 for no heart diseases and 1 assigned for heart diseases. And for the categorical variable coding, females are given a value of 0 and male are given as a value of 1. Moving to this table, which is variable in the equation, this is a very important table, shows here the coefficient value and the test which is used for binary logistic regression, which is called Wald test. Standard error is generated, and degree of freedom, significant p-value, and exponential p, which is the odds ratio. Moving to the section here, which is for method enter, the important table also here, which is the model summary. A model is generated by trying to fit the predictor into the outcome to generate a model in which the possibility of the predictor can predict the outcome. Again, looking at the R square here, which is the value here, which is 0.735. This value means that 73.5% of the variation in the outcome, which is the heart diseases, whether you have a heart disease or not, can be explained by the predictor, which is the sex, whether male or a female. So the sex or the gender of individual can explain the variation in the outcome. Jumping to the last diagram here, which is very important, as shown from this diagram, predicted probability is of the membership for HD. So we are here calculating the probability or the chances or the odds for heart diseases, possibility of heart diseases. The table here is also an important output for the interpretation of the result from the analysis, binary regression. There is a value is given here for the coefficient, the standard error, the Wald test, the degree of freedom, significant as it is less than 0.05, and 95% confidence interval for the exponential, which is the odds ratio. This is for the predictor or the variable, which is sex, and again given a value of 1. Here we are comparing the males to females. So the way to read this result or interpret this result, it shows that there is a significant association between the outcome, which is possibility of getting heart diseases, and the predictor, which is the gender of the individual. As shown here, the males have a 224.5 odds of having heart diseases compared to females. So the males had an increased chance of getting heart diseases with an odds of 224.5 related to the females. So this is the way to perform binary logistic regression with an outcome that is binary, which has 2 levels in it, and a predictor, which is binary, have also two levels in it to find out whether there is a relationship between both variables and whether the predictor can predict the outcome. Binary logistic regression with categorical predictor in SPSS. In this SPSS data sheet, I had inserted 200 cases. We have here two variables. The first variable is smoking. The second variable, whether you have cancer or no cancer. The first variable is a categorical variable. It's multinomial variable because it have in it four classes or four categories: non-smoker group that smokes cigar, groups that smokes pipe, and groups that smoke cigarettes. So there are four classes or four categories in the first variable. So it is multinomial variable with four categories in it. Cancer, whether you have cancer, yes or no. So this variable is binary or dichotomous or binomial. So we have here two variables. One of them is categorical and the other one is binary. So the outcome here is the cancer. So cancer is binary and the smoking is a predictor. To find out whether there is a relationship between smoking habit and developing cancer, then binary logistic regression can be performed to find out whether there is a link or relationship, or whether smoking habit can explain the variation in the outcome or can predict possibility or likelihood of getting cancer. As here the outcome is binary and the predictor is a multinomial. Before proceeding into doing the binomial logistic regression, let's start do some descriptive analysis. If we click on analyze, then descriptive statistics frequencies, select both variables and drag them into the variable box, and then click on OK. Multiple tables will be generated. As shown in the first one, there are 200 valid cases for smoking and cancer and no missing cases. For smoking, there are 200 cases, 50 cases non-smoker, and similarly cigarette, pipe, and smoking cigarettes. And for cancer, 200 cases, half of them have cancer and the other half doesn't have cancer. To do the binary logistic regression with this predictor, which is smoking, and an outcome, which is cancer, click on analyze, scroll down to regression, and then scroll down to binary logistic regression. In this new window here, since our outcome is the cancer, then drag that to the dependent empty box here. And for smoking, since smoking is a predictor, drag that into the covariate. If the predictor was continuous, then also drag it to the covariate. If the predictor also ordinal, then drag it into the covariate box here. Click on categories or categorical. Since smoking have four categories in it, then drag that into categorical covariates, and we are going to set the non-smoker as a reference group, which is given a value of 0. And it's going to be first as selected here. Click on continue, and then click on options. For options, click on classification, click on Hosmer, and click on CI confidence interval for exponential p-value. Click on continue and click on OK. Before interpreting the result, let's look at the assigned value for each categories by clicking on the variable views, and then click on the smoking values. Non-smokers are assigned a 0 value. This is going to be the reference category to compare to. Those who smoke cigar given a value of 1. Those with pipes smoking given a 2, and cigarette 3. So back again to the output for the binary logistic regression. The output here shows that there are 200 cases in the first table with 0 missing values in both variables, smoking and cancer. For the smoking table, again, the 4 categories, each category has 50 cases in it. For cancer, there are 200 cases and 100 cases of having cancer and 100 cases without cancer. Moving to the next section here, which shows that the dependent variable here, which is the outcome, which is the cancer, is assigned a value of 0 for no and 1 for yes. Classification table also shows how many cases are having cancer and how many doesn't have cancer. The next table is variable in the equation. It shows here the coefficient value, the standard error, the Wald test used for doing binomial logistic regression, degree of freedom, significance, and exponential p-value. Scrolling down to the most important table, which is the model summary. This table shows that by looking at this value here for R square, it can be explained that 11.7% of variation in the outcome, or whether you have a cancer or not, can be explained by the predictor, which is the habit of smoking. The next table here, we need this value here to be greater than 0.05. Scrolling down toward the end, there is a graph here. It shows that the predicted probability is of a membership for yes. The most important table in the whole output is the table with variables in the equation. As shown here, we have a categorical predictor with 4 levels in it. The first level, which is non-smoker, are a reference group, which is not showing here. The group which is assigned a value of 1 for those who smoke cigar, 2 for pipe, 3 for cigarette. As shown here from the significance, this one is significant, this one is significant, this one is significant. So there is association or relationship between smoking, whether cigarette or pipe or cigar, with the probability of having cancer. As shown here, the p-value, the coefficient, the standard error, the Wald test, the degree of freedom, and significant. An exponential p, which is the odds ratio. And then 95% confidence interval for the odds ratio is given here, as those two values are significant for determining whether the results are significant or not, the p-value and the 95% confidence interval. The way to interpret the result is by stating that those who smoke cigar have 2.7 odds in getting cancer compared to those who do not smoke or smoke at all. So there is a higher probability that those who smoke cigar will develop cancer, and this is significant. For the second category, which is smoking pipe, as shown here, smoking pipe, those who smoke pipe have higher odds compared to those who do not smoke any kind of tobaccos. So those who smoke whether pipe or cigar are more likely or have higher chance of getting cancer. For the final category, which is cigarette, those who smoke cigarette have 6 times higher probability of getting cancer compared to those who do not smoke at all. So there is a variation in the odds ratio with each categories of the type of smoking, but all of them smoking any type of tobacco products increases the chance of getting cancer. This is the way to perform binary logistic regression with an outcome that is binary or binomial, and a predictor that is categorical or multinomial, consisting of at least 3 categories, to find out whether there is a relationship or association between the predictor and the outcome, and whether the predictor can predict the outcome and the variation in the outcome can be explained by the predictor in SPSS. Binary logistic regression with an ordinal predictor in SPSS. Here in this SPSS data view, I have 2 variables, and there are 200 cases here. Those 2 variables are the age categories and diabetes, whether you have a diabetes or no diabetes. The age category is an age that has been arranged or sorted into categories. The first category is an age of 16 to 24. The second one is 25 to 45. The third one 46 to 70, and the last one is greater than 70 years old. So this variable is categorical variable, but it is ordinal more precisely, as it has categories in it, but there is an order. 16 to 24 is the first, and then 25 to 45 is the second. So this variable is a ordinal variable. The second variable is diabetes, has only 2 levels in it, 2 categories, so it's binomial or binary variable with either yes, you have diabetes, no, you don't have diabetes. So here we have 2 variables, one of them is binary, the other one is ordinal. So the age category is the predictor and the diabetes is the outcome. So to find out whether the age categories can predict the outcome, which is whether you have diabetes or not, or whether increasing the classes or categories of age can increase the chances or the probability or the likelihood of getting diabetes, then binary logistic regression can be used. And since the conditions are satisfied, that we have 2 variables here, an outcome which is binary for diabetes and ordinal predictor which is the age categories. This logistic regression will determine whether there is association between these 2 variables. Before we proceed to perform the test, let's do some statistical descriptive. Click on Analyze, scroll down to Descriptive Statistics, Frequencies, reset this. Drag the age categories and diabetes to the box for variables. Click on OK. Multiple tables are generated. The first one shows that there are 200 cases for the age and diabetes, the 2 variables, no missing values here. The next table is for the age categories from the first category from 16 to 24 up to greater than 70. There are 50 cases in each category. And for diabetes, there are 119 cases of no diabetes and 81 of having diabetes. In fact, before we proceed to the test, let's look at the coding for the variables. For the first variable, which is the age categories, 0 is assigned for the first category from 16 to 24 and 3 for greater than 70. So this value here, 0, will be taken as a reference category for comparison in the logistic regression. For the outcome, which is the diabetes, 0 for no and 1 for yes. Back again to the data view here. To perform the binary logistic regression with a ordinal predictor and a binary outcome, click on Analyze, scroll down to Regression, select the binary logistic regression, reset this. Since the diabetes is the outcome, drag that to the dependent box here, and the age category, drag it into the box here. As shown here in this box, any variable can be dragged in, whether it's continuous variable, whether it is binary variable, whether it is ordinal variable. And since the age categories are categorical, there are 4 categories in it, drag that into this box and select the reference category, which is the first, in this case the 0, which is 16 to 24 will be the reference category to compare to. Click on continue, then click on options, select the classification plots, select this goodness of fit test and confidence interval for the exponential p-value. Click on continue and then click on OK. Multiple table will be generated and a diagram at the end which shows that the predicted probability is of a membership for yes. Back again to the top here, as shown here, the first table shows the case processing summary. There are 200 cases, no missing cases. The second table is coding for the outcome, which is the diabetes, yes or no. Yes for 1, 0 for no. And the next table is for the ordinal variable with the age classes, with the frequencies and the number of cases in each category. Moving to the classification table, again shows those cases with diabetes and those without diabetes. The next table is variable in the equation. P stands for the coefficient, SE for standard error, Wald is the test used for logistic regression, degree of freedom, significant value is taken as P less than 0.05, and exponential P. The most important, in fact, section is the one start from here, in which shows that the model summary. This is an important table. This model summary, this value here, R square, is the one to look at, which says or states that or describe that 25.5% of the variation in the outcome, which is diabetes, can be explained by the age category or the ordinal variable. Moving to this section here, we need this value to be greater than 0.05, and the important table to focus on is this one, the variable in the equation. Again, this table as shown here in the section, this is the variable for age categories. The age category which is assigned a 0 value is considered as a reference, which is from 16 to 24, as not shown here. But the age 1 is for 25 to 45, age category 2 is for 46 to 70, and the last one is greater than 70. The coefficient is given for each one of them, the standard error, the degree of freedom, significance, and as shown here, all the 3 categories are significant, less than 0.05, and an exponential value p value is given here, and as we can see, an increasing value with increasing classes of age, getting older. And then 95% confidence interval is given for each value for the odds ratio. This exponential p is the odds ratio, and here we have 2 layers of determining whether there is significant or not p-value and the 95% confidence interval. From these significant, it is well shown that there is association or there is a relationship between having diabetes or not compared or relative to the predictor, which is the age category. So there is association between these two variables, and the predictor, which is the age classes, can predict the outcome, whether which is in which you probably have a diabetes or not. The way to interpret the result is that those who have an age category from 25 to 45 years old have increased likely of getting diabetes compared to the younger group. The odds ratio is 3.14. In another way, those with a category of age from 25 to 45 have an increased odds of 3.1 to get diabetes compared to the age group which is from 16 to 24. The second category, which is age cat 2, in which the age category is from 46 to 70. Again, the odds ratio is 7.3, so this one is higher than the previous one, and the third one is also higher. So there is a trend of increasing odds ratio with increased age classes. Again, for the age category 2, those with the age from 46 to 70 have an increased odds of 7.3 relative to the reference group, which is a younger group. So there is an increased chance of getting diabetes with increased age. And finally, for the individual who are greater than 70 years old, they have an increased odds of 17.11 to get diabetes compared to the younger group. So the oldest individual have a higher odds, higher probability, higher likelihood of developing diabetes compared to a younger group or younger individual. So this is the way to interpret the output from a binary logistic regression for an outcome that is binary and for a predictor that is ordinal in SPSS. If you find this video useful, do subscribe to the channel, leave any comment in the indicated box, and activate the notification bell to receive the recent and latest release into the channel of several different video clips, and click on the like icon and share the video link with others so the channel can expand and improve to include a large scope of different statistical method and how to analyze data using several different statistical packages such as SPSS, Excel, Stata, Jamovie, R Statistic or Statistics, GraphPad, Prism, GPower, Python, and RevMan. If you are a student or a researcher and you have a data, whether it is quantitative or qualitative, and you want to perform statistical analysis on that data using any of the softwares listed here, whether it's SPSS, Excel, Stata, Jamovie, R Statistics, GraphPad, Prism, RevMan, GMP, Python, then do contact me to arrange for either a one-to-one private tutor session or a training course on any of these statistical packages. My contact details are given here, so don't hesitate to write to me or email me if you need a private one-to-one tutoring or a training course.